Okay, so I just put this together from my class on the board the other day, and I thought it would be helpful just to go over it. So this is just your key items that you should know if you are about to write a chemistry test. It will help you with your exam, so just kind of going over those big items that for sure will be asked. So going through it, your first unit is probably thermochem. Some start with organic, but usually thermo. So starting off with, you want to know the difference between an endo reaction and an exo reaction. So did you absorb energy or did you release energy? Then you have to know this formula, Q equals MC delta T. This is only if you're heating or cooling a substance. So there is no reaction. So it's like aluminum got heated up. What would the temperature change be, or something along those lines? So no reaction. Then we want to see if you change the amount of moles, how does that change the energy released or absorbed to the environment? So the NH equals delta H question, you are getting moles, and then the H that's in the formula is your delta H from a reaction, and it is a molar enthalpy. So if it's asking for more than just 1 mole, you'll have to divide. So don't get confused by that, because even though it's delta H from the reaction, it does not go over into the delta H of the equation. It goes into the H of the equation, and then your result is what's released. Looking at calorimetry, you have the formula NH equals negative MC delta T. The right-hand side is always about the water, and the left-hand side is about the reaction. So if it's asking about just hydrochloric acid, you're finding moles of hydrochloric acid. Now, there are some assumptions you should know. There's 3 of them. Like if you have a neutralization reaction, you still use a specific heat capacity of water, that you are in a closed system, that you're not losing energy, and things like that. You also would want to know if you did have a bomb calorimetry system, you would be adding on another negative MC delta T, and that would account for the container. So now the energy is going into the container. The formula for Hess's, or it's not so much a formula, you want to know Hess's law long, meaning that you're manipulating equations to get to your target equation. And Hess's law short, this one is a formula in its very short form. The delta H of your reaction is going to be the sum of the products minus the sum of the reactants. And you get all these values from page 4 or 5 of your data booklet. Some questions you might have more than one step. It's just putting things together. So usually it's using Hess's law short and then finding the delta H and then using that in one of the other 2 equations we know. For activation energy is EA. If you have a potential energy diagram, so I'm just going to draw a quick exothermic one. If you had activation energy, it's the energy you're putting in to make the reaction happen. So it's that bump in the hill. This isn't the best picture, but hopefully that makes sense. So it is that bump in the hill, and then, usually that would make it disappear, but it's not. And every time you're doing activation energy, it is from the reactants to the top of the hill. If it asks for the reverse reaction, it's from the products to the top of the hill. It has no effect on your delta H. Delta H would remain the same. And then if you had a catalyst, all catalysts do is lower that activation energy, but it does not change your delta H. The next unit is electrochem. In electrochem, you want to know what's undergoing oxidation, what's undergoing reduction. So if you're undergoing oxidation, you're losing electrons. Reduction, you're gaining. If you're undergoing oxidation, you're a reducing agent. And if you're undergoing reduction, you're an oxidizing agent. We want to know the difference between spontaneous reactions and non-spontaneous. So spontaneous means you put your reactants together, you're getting products. Non-spontaneous means you put your reactants together and nothing happens. So with that, we want to know that, because then you can build tables. So if you get a series of reactions, if it's spontaneous and you start to place it to make a table, your OA goes higher than your RA. If it's non-spontaneous, then your RA has to be higher on your table than your OA. And then you can answer questions like, what is your strongest oxidizing agent or reducing agent? When it comes to predicting, you want to see if it's predicting a redox reaction. You want to see what's reacting. So you list everything that is present, including things like water, if it's an aqueous system, or hydrogen ions, if it's acidic. And then you're picking your strongest OA and your strongest RA, and you're getting those reactions from the data booklet, coming up with those half reactions, balancing electrons, adding them together. If you have to balance in acidic conditions, there are a set of rules. So you write out half reactions and then you follow those rules. So like balancing everything other than oxygen and hydrogen, adding in water, adding in hydrogen ions, adding in electrons, and then going from there. We also would move on to oxidation numbers. So knowing your fixed numbers, like oxygen is always -2 unless attached to peroxide, hydrogen is always +1, and so on. Once you know oxidation numbers, then you can balance with oxidation numbers. And with balancing, just remember that you can't rely on inspection, so how you would have balanced in the past. You must use those numbers and look at the difference of electrons and balance that way. You want to know the term disproportionation, which means that your OA and RA are the same compound, and it's undergoing oxidation and reduction. Lastly, there is redox stoic. If it's redox stoic, one of the most common labs is the one with permanganate, that dark purple solution. Know that lab. It is, again, one of the common ones, and it will help you when coming up with those formulas. Now, that's the first half of electrochem. The second half of electrochem is about the cells. So I have, and it's written very small here, but voltaic cells. You want to know how they work. How do you identify your anode, your cathode? Knowing your anode undergoes oxidation. Your cathode is reduction. Knowing electrons always move from the anode to the cathode. You want to know your ion movements. Ions come from the salt bridge. Your positive cations go to the cathode. Your negative anions go to the anode. You also want to know what's increasing and decreasing in mass. So anodes get used up, they decrease. Cathodes get deposited on, so they increase. Sometimes if you have an OA or an RA that is not in a solid state, you'll have to add in an inner electrode. So like carbon or platinum, they are just there to facilitate the reaction, but nothing else within changes. To calculate cell potential, you want the cell potential of your cathode, subtract your cell potential of your anode. I just added on here when I wrote this out, do not change your sign for your anode. So I know that's tempting because in a half reaction for reduction, if you wanted just a half reduction of oxidation, you change your sign. But in this formula for the full reaction, don't change it, just plug it in as you see it. Moving on to electrolysis. Electrolysis, instead of taking like voltaic cells, chemical energy to electrical, electrolysis takes electrical and turns it into chemical. So it's non-spontaneous reactions. It works exactly the same as a voltaic cell once you add in the energy. The only difference is you change the terminals your batteries are attached to. Electroplating is a type of electrolysis where we plate a metal with another metal. You also want to remember the chloride anomaly, meaning if you are undergoing electrolysis, that if you had a choice between water and chlorine, even though water is a stronger reducing agent, chlorine will reduce first. So choosing between those two RAs, pick chlorine. Cell stoic, you only need a half reaction, and you want to remember this formula and go from there. And then lastly, corrosion. That theory on corrosion, like what is your sacrificial anode? How do you protect your cathode and things like that. Our next unit, sorry, my dogs are barking like crazy downstairs. Hopefully we don't hear that. Our next unit is equilibrium acids and bases. So when you start equilibrium, you would have learned 4 points that make an equilibrium system. So it has to be a closed system. You don't include solids. There's a bunch of points there. Just read them over. Just make sure you know them. Then you moved on to the Kc expression. This is my very short way of writing it. You take your concentration of your products, and if there's more than one, you multiply your products together, and then you raise it to the exponent of the coefficient. So for instance, if you had 2H2O aqueous as a product, you put the concentration in that square box, and then you put 2 as the exponent. Then you divide by the same thing, but with your reactants. You want to know how to make an ice table. So if you have an ice table, you know that your I is your initial concentrations, C is your change. It's based on the mole ratio. Reactants are used up, so you subtract them. Products are being formed, so add them. And E is your concentration at equilibrium. The values you get from this section of your table, that goes into your Kc expression. Moving on from ice, the other part is now that we have all these systems in equilibrium, we want to know we can stress systems. You can stress them with a temperature change, a concentration change, or a volume or pressure change, but volume and pressure only affect gases. And then that theory is the only thing that can affect Kc is temperature changes. So the other two, even if there is a change imposed, they won't change your Kc value. If you have a graph when it comes to Le Chat's principles, if you have a vertical line, just one. So if you were in equilibrium, you had horizontal lines. If one of those lines go vertical and the other ones don't, like they changed in some way, that's a concentration change. We're just adding or taking out something within the system. If you have all vertical lines, so all of these are vertical and nothing is gradually changing, then it is going to be a volume or pressure change only if it's a gas system. And that's because everything gets changed at one time. And then lastly, if you don't have any vertical lines, so you have like a just gradual change happening, then that's a temperature change, because we can't just magically change your system in terms of degrees. We have to gradually increase it or gradually decrease it. So those are our lines. The second part of equilibrium acids and bases have to do with acids and bases. So not just equilibrium, but we can have weak acids in equilibrium and then you use the Ka formula. We can have a weak base in equilibrium, you use Kb formula. If you have a system where you need Kb, you can always find it by taking the Kw divided by the Ka from your data booklet. The other part that was mentioned here is this only applies to weak acids and weak bases. Oh, I think my pen just died again. So if you have a weak acid or a weak base, that is what would be happening. If you have a strong acid or base, you can use what you already know. You can just think of your previous chem classes where you plug it directly into formulas, like taking the negative log. But if it is weak, then make sure to use these formulas. The next part we're learning is Bronston-Lowry acids and bases. Here you want to remember that acids donate hydrogens, bases accept. When we're looking at buffers, they both must be weak. If you have a buffer system, you're resisting the change of pH. So if we're adding in a strong acid, it's going to react with the conjugate base of a buffer. If you add in a strong base, it will react with the conjugate acid. So that's why we have a buffer system, to resist change. Again, they have to be weak. They have to be conjugates of each other. So the difference of just one hydrogen. Moving on, before we finished off this unit, we looked at acid-base stoic. Here, we're not looking at Bronston-Lowry. You are literally looking at a neutralization reaction. Don't change anything. Do your stoic how you would have in the past. You want to know your pH curves. So if you were looking at a pH curve, how do you know you're titrating an acid with a base? How do you know you're starting with a strong or a weak acid? How do you know you have only one equivalence point? What happens when you have more than one? If you do have something weak, where's your buffer zones? So things like that you can apply to those graphs. You also would want to know that term amphiprotic, which just means you can act as an acid or a base. Okay, the last unit, which depending on what order you went, might be the freshest, but when you go through this, the first thing you look at is inorganic. So identifying compounds that contain like the CN ion or the carbonate ion and so on. Those are going to be inorganic, just like your oxides and anything ionic. So to be organic, you cannot see a metal. Then you look at all your rules and apply those rules to all the following. So know how to identify your longest chains, when you need to use the prefixes, how you know you have an alkane, so know you have only single bonds. Then alkenes, you have a double bond, and then alkynes, you have that triple bond, and how we name it. You want to know boiling points and how they change depending on what type of alkane, or alkyne you have. You also want to know the terms saturated and unsaturated and how that only affects your carbons attached to carbons in your longest chain. Then once we know what these three are, we can look at what's cyclic. And if you have anything cyclic, you have rings. And if you have rings, you're going to see the word cyclo when you're naming, and that's the main difference. You want to know if something is aromatic, you must see a benzene ring. So looking at your benzene ring, usually you have the circle inside, but knowing that that circle represents alternating double bonds. You want to know the types of reactions for organic, which is addition, meaning you're breaking a double bond. That's what I'm showing here. Elimination, you start with one reactant and something gets eliminated off and you form a double bond and something small. Substitution, you start with two reactants and you end with two products, and within just something swapping places. Combustion is what you're used to. esterification, you have a carboxylic acid in the presence of an alcohol, you make an ester link, and you have water. It's also because you're forming water, a condensation reaction. There is a little bit more theory when it's looking at incomplete combustion, and that's when we don't have enough oxygen to form these products. So when that happens, you have two other possible products, which is carbon solid or carbon monoxide, which is a dangerous gas. You want to know that for most of these reactions, you do need a catalyst, so something to help force this reaction to happen. Then lastly, we looked at polymers. Polymers are formed by addition, so meaning breaking double bonds, or condensation reactions. So when water leaves the reaction and then the rest linked together, either with an ester link or an amide link. An ester link is your carbon double bonded to an oxygen, single bonded to an oxygen, and then we have that link where we can have carbons, or if it's on this side, it could be hydrogen, but this side has to be a carbon, represented by the R. If it's an amide link, instead of an oxygen, you're going to see a nitrogen there. Again, know the boiling points in terms of the theory, and then lastly, being able to understand that polarity within those molecules. So this does bring up like London dispersion forces, dipole-dipoles, and hydrogen bonding. As always, I hope you found this helpful. If you did, please subscribe. If there's any questions you have, you can leave me a comment. And I hope you will check out my website. If you go to this website, you can find specific topics with videos linked. Thank you for watching.